To begin our discussion of counting, here's an outline. We'll look at the fundamental principle of counting. It's a basis for our discussions, and then we'll look at different ways of making selections when order is important, when you're taking things without replacement, permutations, and we'll look at some notation. Combinations will be in the next video. We'll probably look at that in class. So the reason we want to count things, and it's the connection with probability, has to do with the fact that equally likely outcomes situation has us counting the numbers of events and the number of outcomes in the sample space. So we'd like to count these things. More generally, this field is called combinatorics when you start looking at different possible combinations and arrangements of things and ways to make selections. Combinatorics. So here's our fundamental principle. The number of total outcomes resulting from a series of events is found by multiplying the number of outcomes for each event or choice. It's very simple. So if you want to use mathematical notation, you have n1 ways for the first selection, n2 ways for the second, and so forth, and we're just going to multiply these. So as a simple example, imagine you have three choices. You got for dinner, appetizer, entree, and dessert. How many different meals? Well, you got three choices to make, and how many different possibilities are there for each? Well, there are three in the first, three choices of entree. For each entree, or appetizer rather, for each appetizer, you'll have your choice of three entrees, and then two desserts for a total of 18. So you've got 18 different possible meals. Very simple. We can use a tree diagram, the same technique we've used before. And to do this, let's just label our choices here. So the A's are the appetizers, E's for entree, and D for dessert. Tree diagram might look something like this. So you can see each branch would represent a meal. This branch here would be the appetizer, second appetizer, first entree, and the first dessert. Here's another example. You want to select a committee, and they have distinct roles: president, secretary, treasurer. So you have a number of choices to make. Well, 10 people can be president, right? Well, having selected the president, how many choices do you have for secretary? Well, just 9, because one of the 10 is already president. And then having selected 2, there are 8 remaining. So we get a total of 720 possible ways to make this selection. So these types of outcomes are called permutations. And the key thing about permutations, there are two of them. One is that we're selecting things without replacement, and the order is important. Those are the two salient features. And we can think of order and without replacement in the context of our problem because the roles of the individuals were distinct, so the order was important because we imagine selecting the first person as the president and so on. And then without replacement, since the same person presumably wouldn't be serving in two different positions. Okay, and we have a notation for this. So we have little subscript 10p and then subscript 3, 10p3. So this is 10 items selected 3 at a time when the order is important, and these are called permutations, and there's the notation. So here's how it goes. Here's another example. Now we have 6 teams in this league. Okay, so 6 teams could be first, 5 for second, and so on and so forth. We didn't draw the boxes this time. You get the idea. Coincidentally, turns out to be the same number, 720. All right. So this is another situation where it's a permutation, but we're taking 6 items 6 at a time. So 6p6 is 720. So here's a little bit of notation because these products arise frequently in combinatorics. 6 times 5 times 4 times 3, 2, 1. So our notation is the exclamation point when we read it factorial. So 6 factorial is 6 times 5 times 4, etc. In general, n factorial, you multiply n times every successive number down to 3, 2, 1. Okay? And then we also define 0 factorial this way. just makes things work out. So here's how this works out with our examples. 10p3, we know it's 10 times 9 times 8 because we did that using the fundamental principle of counting. But we can rewrite 10 times 9 times 8 like this. Notice all I've done is multiply and divide by 7 factorial over 7 factorial, right? But now what I have on top is 10 factorial, and what I have on the bottom is 7 factorial. So it's 10 factorial over 10 minus 3 factorial, since 10 minus 3 is 7. So notice, well, let's go back here. So it's nice because 10p3 over here can be written as a formula where 10 and 3 both occur in the formula. So in general, here's how the formula works. Okay, so for the bowling league, we know that there are 6 factorial outcomes because we had 6 times 5, etc. Let's see how the formula works out with this. And well, you can see that it does, because 6 minus 6 factorial on the bottom is 0 factorial, and that's one reason why we want 0 factorial to be 1. So the formula works for us.